We want to keep track of what is reacting, how much stuff is reacting. If you're going to count atoms and molecules and ions, it's too much. There's too many small particles. So this is simplified by using the unit called the mole, M-O-L-E. It has a name. It's called Avogadro's number. It's 6.022 times 10 raised to the 23rd power. And I want to let that sink in. That number represents the mole. So when we say there's a mole of something, that's the count. And you can see it's a lot easier to just say how many moles there are than say, well, this is how many atoms are reacting. This is how many molecules are reacting. So that exponential number just gets really, really big. The mole is equal to 6.022 times 10 raised to the 23 of anything. A mole of atoms, 6.022 times 10 raised to the 23. A mole of molecules, 6.022 times 10 to the 23. 5.82 mole of argon atoms. And they want to know, well, how many argon atoms is that? And so whenever you get a question like that, when you actually have to do a count, you're going to say, okay, let's convert this to the number of atoms and cancel this unit. So the mole now is a new unit that I'm introducing to you. So this is the mole unit. Now look at this ratio right here. 1 mole is equal to 6.022, 10 raised to the 23. And that's it. 5.82 times 6.022, where it says times 10 raised to the 23, this is what I want you to use. This symbol right there, that double E right there, second E, and then just 23. So that E here represents times 10 raised to the 23. 3 significant figures, so my answer is going to have 3 sig figs. So this is 3.50, 10 raised to the 24. Atoms of argon atoms. There's this many argon atoms in this many moles of argon. So these are equivalent, right? So this is how many atoms there are in 5.82 moles. So right here, what do you think is going to be less confusing to use in our calculations? When we study reactions, we could use this if we wanted to, or we can just say 5.82 moles. So this is going to be a lot easier to use. Okay, so we want to convert the mole of water molecules to the actual number of water molecules. So look at this ratio. 1 mole is equal to 6.022, 10 raised to the 23 water molecules. 6 second E, so times 10 raised to the 6, that's what it tells me, times, here's another number, 6.022 times 10 raised to the 23. A lot of water. Now, this is 1 sig fig, right? That's my limiting factor right there, 1 sig fig. So right here, 3 times 10 raised to the 30. And then the next number tells me to round up. So my answer here, 4 times 10 raised to the 30 water molecules. For aluminum, the number that's in here is 26.981538. It's a really long number. Well, some of these have shorter numbers than others, but this number is the atomic weight. But this is the most important thing right here. The units, grams per mole. Grams of aluminum for every mole of aluminum. Common practice just to round to 2 decimal places. That's good enough for what we do in our class. So for aluminum, we'll just call this 26.98 grams per mole. Let's convert to the mass. That's what they're asking us. So we're going to convert to grams of aluminum, and we want to cancel this right here, mole of aluminum. Whenever you see this ratio right here, grams and moles, this is not Avogadro's number. When you're looking at an element and it says grams per mole, that always comes from the periodic table. Okay, so that's what this number represents. So we'll write down 26.98 grams per mole. Look at the units. That cancels. We start with 2 significant figures, so my answer should have 2 significant figures, so we'll just call that 67 grams of aluminum. To find molar mass, just simply add them up. So 2 sodiums, let's go find sodium. Again, this might be really small for you, but sodium is 22.99. Again, I'm rounding to 2 decimal places. 1 carbon is 12.01. I'm rounding to 2 decimal places. Oxygen is, actually oxygen's interesting. It's 15.999. So if you round to 2 decimal places, that just gets rounded up to 16.00. Hydrogen, 1.007. So that's going to round up to 1.01. And then here's 10 more oxygens again. We'll call that 16.00. What we have here, we'll call this 45.98. This is just times 1. This is 48.00. This one's easy, right? 101 times 20 is 20.20. And 10 times 16, that's 160. And then just add them up. And so again, to 2 decimal places, 286.19 grams of the washing soda per mole. Pretty cool stuff. So just take 2 times the nitrogen. So nitrogen on your table, 14.01. 1 times oxygen, which is 16. And just add that together. So this is going to be, what is that, 444? Vitamin A is a lot bigger, but don't get scared, right? It's just carbon times 20. So 20 times carbon, we said, is 12.01. 30 times hydrogen, 1.01, and finally 1 times oxygen, 16. 240, yeah, 240O2, 3030, and 16. 286.50. Yeah, make sure you put that second decimal. So those significant figures are important. Let's convert grams to mole of TNT, and let's cancel the gram of TNT. Now, look at that right there. Whenever you see this, this is an important take-home message. Whenever you see the relationship of grams and moles, you're going to say, well, that's a molar mass. And now you know how to get it. Now, this one, let's see, we've got 7 carbons. Carbon, we said, was 12.01. 5 hydrogens, 1.01. 3 nitrogen, which is 14.01. And 6 oxygen, 16.0. That's more like it, 227.15 grams per mole. So here's our molar mass. So really important step here. We have the mass of some compound. We're going to convert to moles, but we're going to do that using the molar mass. And so this is going to be 227.15 for every 1 mole. 4 sig figs, right? 344.6, that's 4. So we'll call this 1.517 mole of TNT, trinitrotoluene. Before we can start studying chemical reactions, we need to understand what a chemical equation looks like. Let's start with an arrow. This is called a yield sign. On the left side, we start with reactants. Depending on the situation, these can sometimes be referred to as reagents or starting materials. On the right side of the yield sign are the products. The reactants and products are written with their chemical formulas. If more than one reactant or product is present, they are included on the respective side with a plus sign. The phases of each species are included italicized in parentheses after each species, where G is gas, L is liquid, S is solid, and AQ is aqueous, or species that are dissolved in solution. Other information can be written on top of or below the yield sign, like reagents. Conditions can also be written. These include the temperature at which the reaction occurs, or added energy in the form of heat or a photon. Delta and H nu represent heat and a photon respectively. Sometimes a reaction occurs best in a specific solvent. In these cases, the solvent can be written underneath the yield sign. Catalysts help reactions occur faster without being part of the net reaction. Catalysts can be written on top of the yield sign. When studying thermodynamics, changes in functions like enthalpy, entropy, or free energy are written at the end of the equation. Here is an example of the change in enthalpy. And finally, balancing the chemical equation. Add coefficients in front of a species to multiply them so that the moles of each element on each side of the yield sign match. Let's understand why we must balance chemical equations. There are two main reasons. First, the law of conservation. Atoms or moles are neither created nor destroyed in a chemical reaction. Atoms are only rearranged. Therefore, each atom must be accounted for during a chemical reaction. Take the example of methane reacting with oxygen to yield carbon dioxide and water. If you count each element on each side of the yield sign, you'll see that hydrogen and oxygen do not balance. We can never change the subscripts of the species. This would change the molecule. We can, however, insert coefficients in front of the species. For example, inserting a coefficient of 2 in front of water means that you multiply water by 2. Thus, you now have 2 water molecules in the balanced equation. In terms of counting moles, we can say that there are 4 moles of hydrogen present on the product side. Notice how the moles of oxygen have been changed as well. There are now 4 moles of oxygen on the product side. We'll need to balance the moles of oxygen next. We can balance the moles of oxygen on the reactant side by inserting a coefficient of 2 in front of the oxygen. All of the elements are now balanced. Notice there is no need to write the coefficient of 1. If no coefficient is present, a 1 is understood. This brings us to the second reason why we need to balance chemical equations. The coefficients in the balanced equation represents the mole ratios of each species in the reaction. This means that the coefficients tell us the exact ratio of moles of species reacting in the equation. If you can understand this concept, you can do any stoichiometry problem. We can read this equation as 1 mole of CH4 reacts with exactly 2 moles of O2 to yield exactly 1 mole of CO2 and exactly 2 moles of H2O. You use these ratios to convert one species to another in a stoichiometry problem. Let's recap. We balance equations to obey the law of conservation. Atoms or moles are neither created nor destroyed in a chemical reaction. Atoms are only rearranged. Thus, we must account for each moles of element. And second, the coefficients in the balanced equation are the stoichiometric ratios. Thus, you can use the ratios to do any stoichiometric conversion. Here are some tips for balancing chemical equations. First, balance pure elements last. Second, when no pure elements are present, balance simple species like H2O last. Third, when present, balance polyatomic ions, not atoms. Let's look at a few examples of each. In an earlier video, I showed the reaction of methane with oxygen to yield carbon dioxide and water. Here, the carbon is balanced, but the hydrogen and oxygen are not. Notice that oxygen on the reactant side is in its elemental form. In other words, oxygen atoms are not bonded to anything else. Only oxygen, O2, is present. Let's balance the O2 last. In this example, since the carbon is already balanced, we can balance hydrogen first. A coefficient of 2 in front of water means you multiply water by 2. There are 2 water molecules. This balances the hydrogen. But the moles of oxygen has changed. There are now 4 moles of oxygen on the product side. We can balance the moles of oxygen on the reactant side by inserting a coefficient of 2 in front of the oxygen. All of the elements are now balanced. Notice there is no need to write coefficients of 1. If no coefficient is present, a 1 is understood. Here is another example of balancing oxygen last. Ethane, C2H6, reacts with oxygen to yield carbon dioxide and water. Similarly, we see that oxygen is in its elemental form. We can balance oxygen last. I'll balance the carbon first by inserting a coefficient of 2 in front of carbon dioxide to balance the carbon. Next, insert a coefficient of 3 in front of water to balance the hydrogen. The carbon and the hydrogen are now balanced. We can balance oxygen next. Notice on the product side, there are 2 carbon dioxides, each having 2 oxygens. This means that there are 4 oxygens from the CO2. There are 3 waters, each having 1 oxygen. This means there are 3 oxygens from the water. There are 7 oxygens total on the product side. There are 2 oxygens on the reactant side. This is why we save the pure element for the end. We can always insert a coefficient in order to balance the equation. In this case, we need 7 oxygens on the reactant side. 3.5 or 7/2 will give us 7 oxygens. Notice there's a fraction as a coefficient. It is customary in general chemistry to report coefficients as whole numbers, so we can multiply all coefficients by a constant to get a whole number. In this example, we'll multiply all coefficients by 2 to get a whole number. The equation is now balanced with whole numbers. Let's consider another example where there aren't pure elements present. Here we see the example of iron 3 oxide reacting with nitric acid to yield iron 3 nitrate and water. There aren't pure elements present, but we see a water, and I'll balance water last. Another thing you'll notice is that there's oxygen everywhere. Trying to balance an element that appears all over the place can lead to confusion and headaches. I do see, however, there is a polyatomic ion, nitrate, present on both sides of the yield sign. I can balance the nitrate ions instead of the oxygen atoms individually. I'll start by inserting a coefficient of 2 in front of the iron 3 nitrate to balance the iron. Next, I'll balance the nitrates by adding a coefficient of 6 in front of nitric acid. The iron and nitrate are now balanced. The only thing left is to balance the hydrogen and oxygen in water. A coefficient of 3 will do that for me. The equation is now balanced. Let's recap. First, balance pure elements last. When no pure elements are present, balance the simple species, like water, last. When present, balance the polyatomic ions, not the individual atoms. For first-year chemistry students, it is likely you'll find yourself in a loop at times. If you ever find yourself going in circles, stop, take a breath, and start from the beginning. Having a slice of pizza and ice cream might help too. It looks messy. There's a lot of nitrogens, there's a lot of hydrogens, there's a lot of oxygens, and there's oxygens all over the place. Look at that. Phosphate has oxygen, nitrate has oxygen. On the product side, you have oxygen all over the place. When you want to balance equations, you're going to make life a lot easier on yourselves if you identify, are there any ions present? Are there polyatomic ions present? And there is. If you look closely, there's ammonium ions, there's phosphate ions, there's nitrate ions. Notice how phosphate is still phosphate on the product side. Ammonium, NH4, is still NH4 plus on the product side. Nitrate is still nitrate on the product side. So this makes our lives a lot easier. Instead of counting nitrogens, which are all over the place, instead of counting oxygens, which are all over the place, if you can identify the polyatomics, right? If there's polyatomics present, well, then let's just count the polyatomics. There's 3 ammoniums, there's 1 phosphate, there's 1 bismuth, and by the way, bismuth is a 3 plus, right? Because we know that because nitrate is a 1 minus, and there's 3 of them, and there's 3 nitrate. Over here, there's 1 ammonium, there is 1 phosphate, there's 1 bismuth, and of course there's 1 nitrate. You're going to laugh at how easy it is. Just put a 3 right there. This becomes 3 ammonium, and this becomes 3 nitrate. And that's it. Tell all your friends how easy balancing equations is. Call them now. Call all your friends. I hope actually by the end of this you like balancing equations. I know some students just hate it, but I like having fun with it. It's like a puzzle to balance equations. Yeah, okay, so the strategy here, again, look, I see oxygen by itself, I see nitrogen by itself. After oxygen, after nitrogen, anytime you see waters, that's always a good thing to leave for the end, waters, because once everything is balanced, you can always balance the kind of hydrogen oxygen at the end, that 2-to-1 ratio. You can put a number in there and balance it. That oxygen, nitrogen, I want to save that for the end. Let's do the carbons. Yeah, there's 5 here, there's 1 here, so we need to balance using 5. So when we do this, this becomes 5 carbon, 11, oh, okay, hydrogen. And so to make this into a 13, 6.5, yeah, that's a 6.5. That's a 6.5. Now, again, for everyone watching, this is a fraction. We're going to get rid of it at the end, so don't worry about it. So let's see, the carbons are okay, the hydrogens are okay. We'll change the nitrogens in a second. And then the oxygens are going to get out of balance too, right? So let's see, 10 and 6.5, you'll call that, 16.5. Just ignore that right there. Ignore that. And I understand there's a fraction there. Let's get rid of it. So how do we get rid of the fraction? let's multiply everything by 2. Okay, so watch what happens. Let's do this. 2C5, H11, and H2 plus O2. Again, don't put a number in there because we're going to change it anyways. So we're going to put what number we need to put into that lone element to fix it, but everything else will keep it the same because everything else is balanced, right? I mean, the carbons are balanced. This is a 10 CO2. This is a 13 H2O. Yeah. This is easy now. So watch this. 10 carbon, 26 hydrogen, right? 11 and 2 is 13 times 2. There's 2 nitrogen and 2 oxygen. On this side, watch this. 10 carbon. There's 13 times 2, 26 hydrogen. So do you see what happened there? We're good. We're good. Oh, watch this. 2 nitrogen, right? Just by leaving it alone, look at what happened. And so I think you know what to do now. Let's see. 20 and 13 is 33, right? 33 oxygen. Yeah. 10 times 2 is 20. 13 times 1 is 13. That's 33 oxygen. So now everything, look at that. Carbons are good, hydrogens are good, nitrogens are good. So we want this number to be 33. 16.5. But yeah, notice what happens here. So this is a 4 C5, H11, and H2. This is a 20 CO2, 26